mathematical constructs which allow us to, which will allow us, because we have not done much detail so far, allows us to deal with arrays of data. It's better to call it data, and to extract information, and also to try to do dimension reduction, as we tried to explain it the last time when we introduced the major topics of this course. And at the same time, we can also use it for extracting important features or patterns in our data. Now, but rather than this, the idea of matrices and vectors. So for a moment, we said that we're going to work on matrices, okay? On matrices. For today, a matrix is a construct which we can denote it like this, okay? It's a double-sided arrow which denotes any array of numbers, which would be this 1, 3, minus 1, 0, 1, 2. Now, today, we're going to spend some time into talking about vectors. Okay, a vector, it's a vector that derived B. So this is a vector, and a vector B is anything that looks like this. 1 minus 1. Okay, and then with a vector, we can define how we can think about a vector. Then with a combination of vectors, we are going to report that we can define planes. Okay, we can define the equation of a plane, and now this equation of a plane, this is defined as the, let me call this one B is equal to B1, C1 B1 plus C2 B2, where C1 and C2 are real numbers. Okay, they can be positive, negative. It doesn't have to be a natural number. It doesn't have to be an integer. But we see that from matrix we can simplify and get a vector. A vector is an element which has a single row or a single column. Okay, but not both. Then combining these, we can get the equation of planes and much more. So we're going to cover these topics today, and we can start right away with downgrading from a matrix to a vector. Now, vectors, I can also, okay, now let's think about this one first. A vector in R² space, okay? In R² space, we denote the two-dimensional space, which can be shown by the Cartesian coordinate system. And Cartesian coordinate system, it's composed of two major axes, which is the x and y, and they are orthogonal. And orthogonal, they are 90 degrees with respect to each other. They are conjugate. They are reciprocal. We can denote it also like this, reciprocal. Reciprocal, actually, it's a bridge between simply being orthogonal and also sending this information to the new domain. This new domain, it's a concept which you are going, as computer engineers, you are going to see this one probably in third year when you are going to analyze a signal or a data. Okay, so maybe I can write a couple of these. So it could be conjugate and orthogonal. With orthogonal, we need this one when we deal with vectors for reasons that will become obvious pretty soon. Now, imagine that here we have a point 1 minus 1, but let's assume we have a vector C. This is a capital C, which has, let's say, 1, 3. Okay, so this is a vector of 3, and this we can denote as here we have 1 unit along the x-axis. Here we have 1, 2, 3. So this is our this is a pair of numbers which constitute a vector, and it can be shown here in the Cartesian coordinate system like this. Now, I can ask you this question: what is the union? What is the union of What is the union of points which are defined by a constant c times the vector c, where the little c is any real number? So what is this? This is equal to what? That's the question. So again, what is this vector c? It's just this point. I don't have a different color pen, but it's this point. So let's see what we get here. Let's assume that c, this constant c, is equal to a series of numbers. Maybe it's better if we write this one like this. Let it be 0. Let it be 1 over 2, 1, 1/3. So we can make up some points, right? And by the way, before we conclude to this one, can anyone answer what do you think could be the union of any constant c times a vector c? And with union, this means that we gather all the possible points and we try to construct a set. Mundohemi të bëjmë një bashkësi që është shumatoria e gjithë pikave që na interesojnë. Let's assume we get here 0. What is 0 times 1, 3? 0 times 1, 3, we get this point here. Okay, we get this. Then, when c is equal to 1 over 2, we have here 0.5 times 1, 3. And we know that the multiplication by a constant with a vector, it is defined as this constant multiplying each of these elements. Okay, so this 0.5 times 1, 3, this would be equal to 0.5 and 1.5. And this point here, it would be this point here. Okay? Then we can put c equal to 1, which is this other point. C equal to 1/3. What is 1/3? We get here 1/3 down here. 3 times 1/3 is 1. So we get this point here. So it looks like as we change the value of c, the value of the constant, we have the chance to get another point here, another point here, here. And if we get all of these, what do we get?
The vector.
A line.
A line. Okay. So here we can get a line. Okay. So that's good. But now, the first question that I can ask to you is the following: does this line pass through the origin?
Yes.
Yes.
It does. Okay.
Yes.
So this one passes through the origin. That's correct. And now we can define. We have a couple of new joining. So we can also. So let's write it like this. This is a line. We did it correctly, and let's pass it through origin. Okay. And now we can define another line which can be written like this. Another line, let's call this L, is equal to a vector P plus a constant C times P. Okay, I just came up with these, but P is any vector. And now, what this would be a line which passes through a point P, which in this case, if this P is 0, 1, plus any constant C times, let's assume, what was this other vector? It was 1, 3. So here we have 1, 3. And then we have to find out what is where can we find this line L. This line L is going to be equal to this point here. So this is the point, the 0 vector, or the, let's go here. So this is 0, 1, and then we're going to have the same line with the same slope, but passing through this other point. So, and also, we can see that this line here, let's call this one L2, okay? And then this other one, C times C, or let's call this one C times C, let this be L1. Let's call this one, I call this one initial C, but let's call it T, because or assume that this capital C is equal to vector T. It should not be very difficult. And then here we have this T again. And we can see that line L1 and L2, they are two lines which are parallel to each other, but one of them is passing through the origin, the other one is passing through another point 0, 1. And also we can add that this is not the only equation to represent line L2, and I'm sure I'm sure that it's also clear that L2, we can write this one also as we can pick up any other point along this line and we can add. So let's try to find another point where this would pass. So let's find, for example, let's set for C equal to 1. What is L2? Can you answer this?
1, 4.
That's correct.
1, 0, 1 plus 1, 3 equals.
Okay, that's 1, 4, which means that this L2, this can also be written as 1, 4 plus this vector. So we can write this one as 1, 4, but now we can take the transpose. Okay, when we write this as a row, this is the transpose of a column. And this would be plus CT, okay, where T is again this reference vector. Okay, so this is how we can define the line. So what was it? It was a union of points that satisfy this condition. Okay, this is. And by the way, I just want to ask: is the light on the board too much?
No, it's okay.
No, we can see.
Oh, it's perfect.
It's good because I have a lot of reflection. Is it better now?
Yes.
Yes.
Okay, thanks for the feedback. And so here we have the equation of a line. Yes.
Can you explain the part where you wrote 1, 4 to power T?
Yes. I just wanted to say that so far, thank you for the question. So far, we are writing the vectors as columns. This is a column vector. This is a row vector. But the transpose of a row vector is equal to a column vector. Last time, we discussed about the transpose of a matrix. And actually, I made a mistake. I should not have erased this A. But let's assume that A is 1 minus 1, 2. 0, 3, minus 5. So this is a matrix which is, what is the dimension of this matrix?
2, 3.
What?
2 by 3.
That's a pure matrix.
2 by 3. So here we can say that A transpose, it should be, what is the
3 by 2.
The rows become columns, okay? So this is a row, 1 minus 1, 2. And now this will be a column, which is going to be 1 minus 1, 2. Then we look at the other row, okay, 0, 3 minus 5, and we make the second column, 0, 3 minus 5. So this is the transpose of this matrix. Now similarly, if we have a vector B, which is equal to 1 minus 1, 0, the B transpose is equal to 1 minus 1, 0, okay? So this is 3 by 1, this is 1 by 3, and this is also a reminder of how we deal with transposes, okay? And here I didn't have space, and I wrote it like in here. So if Fermat knew the transpose, he would have solved an interesting problem. So there is in mathematics, there is a list of people who could never prove their theorems, okay? The one leading the list of mathematicians that have very beautiful theorems, but they can never prove them, is Fermat. Fermat, he was a lawyer, and but he loved mathematics, and he has a lot of theorems. And once he, like 350 years ago, at the edge of a book, he wrote a very interesting theorem. and he said that I know the proof, but I don't have space, okay, in this at the edge of the book. In fact, maybe he never knew it because it was proven 350 years later after his life. But so here we ran out of space and we were forced to learn to discuss about transposes. And Fermat believed 350 years ago he could not have used this transpose thing because linear algebra was not existent back then. And we learned that this is a new topic. So, okay, so far we discussed the union of a single vector times a constant. We discussed which was a line, okay? Now we can also define a new construct, a little more complex construct, which can be like this. Imagine for a moment, this is vector t, and let's define another vector, which is, let's say, minus 3, 1. And let this be equal to vector v. Okay? And now, if we look at these two vectors, what information can you extract regarding these two vectors? I see a couple of comments here. Let me. Okay, Cleo, we're gonna see your comment during the break. Okay. Okay, so we give here two vectors. What can we see from there? Some people. This is minus 3, 1. This is minus 1, minus 3, 1. So we get the vector, which is going to look like this. Okay. So the vector t.
They are perpendicular to each other.
Yes, that's correct. Okay, so they look like they're perpendicular. You guessed it right. So let's see now what could be. So they are orthogonal. They are perpendicular. That's good. Now, what could be the union? What is the union? Or what is a set which is composed of all the possible points, which is described by C1 times T. Maybe it's better if I take out this capital C. Maybe T and V is a better terminology. Plus C2 times V. Okay. What is the union of all of these points? What we can do is the following. Let's assume C1 or let's write it like this. Let's C1 and C2. Let them be equal to 0, 1, 1 over 2, 1 over 3, 2, so we can make a series of these, and let's try to identify, so when C1 is equal to 0, and C2 is equal to 0, I guess we get the origin here. When C1 and C2 are 1, we get this coordinate in the Cartesian coordinate system that might look like this. We get this point here. Let me erase the y-axis. So this is this is the y-axis. This was vector t, okay? This is vector v. And then when we have C1 and C2 both equal to 1, the new point, it will be t plus v. And this is where this will end up. So we have this point, this point. When C1 and C2 are 1 over 2, we have halfway of these, and we get another point somewhere here, okay? And then we can set C1 is equal to 1 and C2 is equal to 0. Then C1 is equal to 1, C2 is equal to 0. We get this point here. If we change C1 and C2, we can find this point. So what do you think one can get if we collect linear combinations, or if we consider all the points whose location can be defined as a function of t and v? Even a point here, one can write this point as a function of t and v.
We can get a plane.
Let's see the initial question. So we said the union of these, this is a question mark. That's correct, this would be a plane. So we can get a plane, and this plane, it is, we can call, so this plane is spanned by T and V, okay? So with the term span, this means that we can define any point in this plane as a function of these two given vectors. Or we can say that T and V span the plane. Okay? So T and V span the plane, and we see that these two, the plane, what is the dimension of the plane? It is 2D, right? It's two-dimensional, and it looks like we can span a two-dimensional structure with two vectors. Then we had a line which was spanned by a single vector, and we saw that we could have lines that pass through the origin, which would not have this constant vector p, okay? It would have only c times t, or it could be a line which does not, that passes through the origin and does not pass through the origin, so we can construct a lot of lines, but these are all one-dimensional entities, okay? But the planes are two-dimensional entities, or spaces, or sets. And then, similarly, we can follow a third argument by defining a vector w, which can be equal to, you can give me a number, any number that you can come up with, like 3, 4. 3, 4, okay. So we can define another, but here I might correct a little bit or improve our discussion, because if the 3, okay, that's good. Maybe we can correct my initial effort as we go along this one. So let's assume we get 3, 4, okay? Where is 3, 4 in our graph? This terminology, we're going to repeat this again, and you're using 3, 4 is 1, 2, 3. 4 is 1, 2, 3, 4. So we get a vector which is going to be somewhere here, okay? So, what could be the union of, so let me take this out. What is the union?
With this space this time?
Think about this one, just allow me 1 second to write this. So that if we have C1T, C2V plus C3W. So what is this? And can you repeat this again? Sorry for interrupting you. What
With this space,
is going to be what?
the space up here.
But which space? What dimensional space? How?
3-dimensional?
Three-dimensional.
Okay.
Three-dimensional. We only got two coordinates.
That looks right. The last statement. Think about for a while what your friend stated. He said that we have only two coordinates. That's true. So the union of this C1T plus C2V plus C3W, where W is here on the board, what can we spend? Can we spend something better than what this was doing? So let's compare how well we are doing when using this versus this. Are we adding some new information by having on the board also the W?
The span is going to become bigger.
The what? The space?
The plane, my bad, yes.
The plane. Actually, this plane that we did pretty well in determining by this is a whiteboard. Okay, let's have a look at the whiteboard and all the points on the whiteboard, even this one here. So this point here, we can easily span by these two initial vectors, because we can have like this distance from here, from origin to here. Then we can take this vector this way up. I don't want to write on the wall, but so any point here on the board, this one, or this point here, or down here, we can define it with T and V, okay, with the previous one. But now, when we added the W, are we covering much more points? Are we defining more points?
Yes.
Yes.
But tell me one point on the board which we cannot describe as a function of T and V, but we can describe as a function of T, V, and W. Tell me, should I move left?
It's points out of the board because every point in the board can be described with two vectors.
Any point on the board can be described with two vectors. That's true. Now, so did the W add anything new?
No, for the board, no.
No, that's correct. So the third vector, since this one itself is on the board, we can call this one W is, we can use a couple of words, but few, but I can pick redundant or useless. Okay, it's a useless piece of information because it's not adding any new dimension, this W. Because W itself, it can be written as a function of T and V already. Okay, so this new point that we came up here, this is linearly dependent on this initial T and this initial V. Initially, we had T and V, and we said that the addition of this vector V, it adds a lot because the vector V, it cannot be expressed as a function of T, okay? We could also see, what about this one? I can ask another question. What could be the union of points? So let's assume we have T, which is equal to 1, 3, and WL, let's define a vector L, which is equal to 2, 6. What is the union of T and L?
The union of all points, all vectors A times T, where A is a real number.
That's correct, but what is it? Is it a line? Is it a plane?
A line.
A line.
Can be considered a plane on high-dimensional spaces.
Why isn't it a plane?
On R square,
Because
it is
they
a
are
plane.
parallel.
On
One at a time.
One at a time? Okay, I can keep this according to the alphabet. So let's start from A. Albi Tsitsi. Then it's Alexandro Beduli, but let's start with Albi. Albi, why these two vectors, T and L, cannot define a plane? Mumbaraj Kumsi. Pasek Alexandros, if you didn't list. Why T and L cannot define a plane?
Can I answer?
Yes, you can.
Yeah.
It's more of a supposition, but L can be defined as 2T, where 2 is the constant.
That's true. That's true. So L is equal to 2T. So in fact, since L can be described as a function of T, this is really still, it's not any new piece of information. So it's redundant again. So let's not forget. So the union of T and L is equivalent to the union of T and 2T. Okay, and the T itself is a line. 2T is the same line. So the union of these two is still a line. We can write here, it's a line, which was, again, we could describe the same line using the single vector T. We added a second one, which is in principle already written as T itself, which means that L in this time, L is redundant. So we can say here, or let's call this useless. Or adding nothing new, okay? It's not adding anything new. So from this discussion of vectors, we are also getting a feeling of the concepts of space or dimensions of space. So I think with these few examples, it could be clear to us that at this moment, the union of C1T plus C2V plus C3W is still the whiteboard. So then we can try to generalize a little bit our discussion, which would be the following. So let's say that we have a vector T1, which is equal to 1 minus 1, 0. T2, which is equal to 3 minus 1, 4. And T3, this would be equal to 1, 1, 1. Okay? So this time, we can keep asking the same question. What could be the union of the first two vectors? Let's look at these two first.
It's still a plane.
It's a plane, that's correct. What is the union of T1 alone? So let's assume we have only T1. We have only this.
Line.
That's correct. T1 alone is a line. T1 and T2, it constitutes a plane. And
We
then
have space with T3.
we have two-dimensional space. If we add, what would be the union of T1, T2, and T3?
That's
Three-dimensional space.
That's true. This would be the three-dimensional space, because now we can say that we can write the following. Now we use this part, we can say that T1, T2, T3, they span three-dimensional space, 3D, okay? Which means that the volume in the classroom or in your rooms, any point in the room, it can be defined by these three vectors, okay? Now, imagine if we have now, we are still learning basic things which are vectors. But at the same time, we are covering too much information which we're going to discuss in details in a few weeks from now. But I think that this is not essentially very difficult. So we can really discuss this because from an early discussion of how we are approaching the vector issue, we can understand actually also the topic of spanning a certain space. So, okay, so these are with what we said so far. We discussed actually the vectors in R square, and I can write this on the board. So we see here T1, T2, and T3, they span 3D. So until now, we have discussed the vectors as in R squared and the vectors in R cubed. So any vector in R cubed, which would have a triple of numbers. So a vector in R3 we define by a triplet of numbers. A vector as a subset of R squared, it would be a pair of numbers, okay, which can define a point in the Cartesian coordinate system. And this is what we can get so far. Now, these vectors, I think we, before discussing in detail the spanning of spaces by a vector, it would be good if we cover a couple of important properties of vectors, which in principle are very similar to the matrix operations that we did the last time. So we know that. So when we were defining the points in this plane, we said that we write them as C1T plus C2V. Let's get this part out. And let's ask, for example, what is 2T plus 3V? What is this? T and V there on the board.
The sum of the two vectors.
But we do here 2 times 1, 3, plus 3 times minus 3, 1. Okay? And this would be 2 times 1, 3. This is 2, 6. Okay? Plus minus 9, 3. And this would be equal to minus 7, 9. Okay, so this is how the 2t plus 3d would be. Then we can also find what is t minus v. What is t minus v? This would be 1.
Vector.
It would be 1. let's see. We have here minus 3, 1, and this would be equal to 1 minus 3, we get 4, and 3 minus 1, we get 2, okay? So t minus v, we got here 4, 2. Where is 4, 2? 4, 2 is somewhere like 1, 2, 3, 4. 2 is 1, 2, it's here, okay? So it's a vector which is somewhere here. If we want to show this one in space, we could define this as follows. So this is the vector t minus v. Where is v? V is this vector which starts in the origin and ends up somewhere here. And this vector v, we can move this one parallel, keep in the same direction. This is also v, okay? I can bring this v up here. This is also v. I'm keeping these lines parallel to the initial v, so these are all v. This is also v, okay? I try to do the best drawing them to scale. But if we change the direction, this becomes minus v, okay? And this is also minus v. This is minus v. So then t minus v, I can bring, so this was a t, okay? Then we can bring the minus v here, and this is what we get. So this vector here is in fact the t minus v. So this is how we can add or subtract two vectors in a plane. Now, similarly, we can also define the addition or the geometric representation of the addition of few vectors. We can denote it like what we're going to do now on the board. Imagine that we have a vector here, a vector t1, so t1, then we have a vector t2, and a vector here t3. The addition of t1 plus t2 plus t3, this is defined as, let's bring vector t, let's put the coordinate system here first. We have here t1, it's something like this. I try to draw it as best as I can. t2 is a vector which goes like this, and t3 is pointing down like this. The result is going to be a vector which is between these 2 points. We start from the end of the first vector to the tip of the last vector. So this is the end of this vector, this end point here, and this is the tip of the vector. And when we add vectors together, we just put them in a row. We say t1, this is the tip of t1. Then we bring the end, put in a vector, we bring the end of the second vector to the tip of the first one. Then we bring the end of the third vector to the tip of the second one. Okay, so this is how we do. And finally, we get a vector which is going to look like this. Okay, let's write this one t4. So t4 is this vector here. Now, we can try to do a slightly better draw, which, and with this, we mean we can draw this a little better because we use this extensively. So let's assume, let's give, for example, t1 is equal to 3, 4. t2 is equal to 1 minus 1. t3 is equal to 2, 1. So let's add these 3 vectors. Where is t1 is 3, 4. This is 3, 4 is 1, 2, 3. 4 is 1, 2, 3, 4. So we get 1, 2, 3. We get this point. This is t1. Okay. This is t1. t2 is 1 minus 1. 1 minus 1 is this vector. So we got 1 unit along the x and 1 unit along down the y. So we get a vector which is somewhere here. This is t2. T3 is 2, 1. 2, 1 is this vector here. Okay? Then, so these three vectors are shown on the board. Now, if we want to do T1 plus T2 plus T3, let's do this T1 plus T2 plus T3. What we can do is that we assume that these are vectors, okay? So if these are vectors, we are very good at adding these vectors together. So just looking at the numbers, what can be the result here? Alexandros, can you, I want to ask Alexandros here. Let me see here. Alexandro Beduli. Alexandros is not, Alessio? Alessio, the Arbin Bici? Alessio?
Yes.
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 Alessio, so what would be the answer here? So if you have T1 plus T2 plus T3, what do we get?
I don't.
6.
What?
6, 4.
6, 4.
That's true. But unless you can add here 3 plus 1, 4 plus 2, 6. Okay.
Okay.
Okay. Then the other element, it's 4 minus 1, 3
Plus 1, 4.
6, 4. Okay. So this is the answer. Now we did this just by doing matrix addition. We could also do it this way. T1, by analyzing based on the geometry, T1 is this vector plus T2. Let's carry this T2. Simple vectorial. Mare fundini vectorial, dhe vendosim te maja e vektorit të parë. Ne vendosim rrjeshtë, njëri pas tjetrit. Si vagonat e trenit. So we get here, this is T1, T2. Let's carry this vector here, this one here. Let's bring it here. And this one moves 2 units along the x.
Professor, that's not T2, that's T3. If
Is it? Okay, let's go. Yeah, that's wrong. So T2, but actually T1 plus T2 plus T3.
Change the thing.
yeah, I could. Yeah, we could.
You are right. So we could do it either way, but let's pick up T2 then. T2, from here, it would move 1 unit this way, 1 unit down, okay? So it is vector here. So, and then we will have also T3. T3, we have to pick up now this vector which we incorrectly tried to add before. So we carry this one from here, we bring it here, which should be, we move 2 units this way.
Wait, why are you doing this?
We're trying to add the vectors by using the geometric representation, okay? Assuming that they are vectors in a 2-dimensional plane. Okay, we're just, this is an exercise to understand both vector addition and also space analysis or space spanning by a few vectors. Okay, so it looks like we were here, this was 3. When we added the T2, we went to 4, and then when we added the T3, we added 2 units, so we got here 6. And we noticed that, wait a second, is this correct? Yes, I think it is correct, so we get 4.
Aty deri sikur të dyshi është useless.
Cila?
Të dyshi. Po ta bashkohesh fillimin e të parë me fundin të tretit deri sikur të dyshi është useless. Është sikur të njëshi bashkuar me të treshin.
No, it's not exactly useless because T1 plus T3, what is it? T1 plus T3, we have this, so this is 5, 5, right? T1 plus T3 is 5, 5. T1 plus T2 plus T3 is 6, 4. So it's not useless. You can say this, that in order to span the 2-dimensional space, you can pick up T1 and T3, you can throw away T2, okay? But, okay. So let's move again, and let's see. So I hope this was probably this was already clear from the last week discussion, but we cover this once again. Now for vectors, we can define some, let's discuss about the multiplication of vectors. And let's see, for example, what is T transpose times V? What is the dimension if we multiply the T transpose times V here? Or before we do this,
It will be 1 by 1 matrix.
that's correct, it's 1 by 1. Why is it 1 by 1? Because T transpose, first of all,
It's
what is the dimension of T?
1 by n.
No, dimension of T is 2 by 1, sorry, I just came back for a moment. V is also 2 by 1, which means that T transpose is 1 by 2. Okay?
Times 2 by 1 is 1 by 1.
That's correct, 2 by 1. And when we look at the multiplication, the first thing we check is we check whether these two dimensions are equal. They are, which means that the multiplication is defined. And then the answer is going to be a matrix, okay? A matrix which has dimension of what?
1 by 1.
1 by 1. And a vector, sorry, a number, any number, it is a matrix with dimensions 1 by 1. Okay? So we can say that when we multiply the T transpose with V, we get a number. But if we get a number, this means that this is not a vector. If it's not a vector, we can call this scalar. This is a scalar quantity because it's simply a number. And the number, it is defined as a matrix with dimensions 1 by 1. Okay, that's good. So let's see, but what is the answer? So can we find what is T times V?
Professor, I have a question.
There's a question.
I have a question. Yeah, so we get the row from the first one and the column from the second one?
Yes.
The number of columns?
Yes, because T, what is the dimension of T? Ca 2 riește în column, it's 2 by 1, right?
Yeah.
Okay, so the transpose should be 1 by 2. So it becomes the column vector, it becomes a row vector.
Yeah, but when we multiply,
yes,
we got 1 by 1 in the end.
Yes.
So the number of columns is taken from the first one, and the number of rows is taken from the first one, and the number of columns is taken from the second one.
Yes, you can say so. Yes. This 1, 3. This is 1 by 2. This is 2 by 1. And how do we multiply two matrices like this? We multiply element-wise pair multiplication. So we multiply this row with this column. So what do we get then?
0.
0.
What do we get then? What is the answer?
0.
Okay, we write this 0. So this is 0, but we can also simply write 0 with no matrix notation, right? So it looks like we get a number, which is a scalar. And we got a 0 because luckily, when we started the discussion of these, we picked two vectors that were perpendicular. And now this is the product between two vectors. Now I can also ask you this, what is T times V? Where?
It's not defined.
We can't multiply.
That's true, this is not defined. We cannot do this. Now, since we are talking about the multiplication of vectors, we can define inner product. Inner product, it is, we can write this one as, so you know what the answer is, I can erase this one. So a very important concept in vector manipulation or the use of vectors is the inner product. Inner product, this is also called dot product. Okay, or scalar product. product scalar, also dot product, it's an inner product, which means that if we have two vectors, if we find their inner product, we get a scalar quantity. Now these concepts, you can see these in physics. You are taking now general physics, where you are going to see that some quantities would be equal to the inner product of two vectors, like the work tuna, it's equal to the dot product between the force and the displacement. So this is what where you can see this inner product or dot product or scalar product. And in principle, this scalar, this means that we get just a number. It does not have a direction. Yeah. Any comment?
We can also define the cross product.
Yes,
two vectors.
That's true. We can also define the cross product, which is which we are going to deal with this one when time comes, I believe. Okay, but for the moment, let's say that this is the inner product. Now, the inner product, if two vectors, let's pick up another vector actually. So here we have 1, 3. Let's find another vector 1 minus 1. So here we have 1 minus 1. So let's do what is the inner product between t and t1. T and t1, in fact, the inner product, we write it like this. Okay, this is how we denote it. We denote with these brackets, which are these brackets which look like the smaller sign and larger sign. This is defined as T transpose times T1. Okay, and what is this equal to? T transpose is again 1, 3 times what was T1? So no, we said no.
Minus 3, 1.
No, sorry, 3, 4.
3, 4.
Okay, let's pick 3, 4. Okay, this is 3, 4. And this would be equal to 9. One times 3 plus 3 times 4. So this is equal to 3 plus 12. This is equal to 15. Okay, we found this. So this is the inner product. Now we can define also the inner product of a vector with itself. This we don't need.
Can I ask a question?
Sure. Yes.
So the inner product of two vectors is always the transpose of the first times the second?
Yes.
Okay.
Yes, it's a good question. It's by convention. A vector we denote it as a column. Okay, let's say it simply. Okay, this is a vector, and it's a column vector. This is also a vector, but it's like vectors. Traditionally, we assume that they are like columns, standing straight. Okay. I mean, it's not that the row vectors are not vectors, but when we discuss this from the perspective not of the matrices, but from the perspective of vector, this is how we define it. Okay. Yeah. So we can also define TT. So what is this? What does this mean to you?
Transpose of T times T.
That's true. But this is at the same time, this is the inner product of T. So or inner product with itself. So this is equal. T is 1, 3 times 1, 3. What is this equal? This is 1 times 1, 1 plus 9 is 10. Okay. Now, I don't need to write it before because we have this here. Yes, we have a question.
What if the vector t is a row vector? Would there be any need to write the transpose of it?
Now, if t is a row vector, let's see. T is a row vector. That means any vector which is 1 by 3. Okay. Can we multiply this one with so this is t. This means that t transpose would be equal to what? 3 by 1. Okay. And then, if you want to multiply it with anything, you just have to be careful with the dimensions that you are holding in here, right? So for a moment, let's see what is t transpose times t. But t now we are defining like this. Okay, forget the previous one. This would mean that t transpose is 3 by 1. T is 1 by 3. So what is the answer here?
will be a 3 by 3
matrix.
matrix.
That's correct. So we get another matrix. Let's write this on capital P, which is 3 by 3 matrix. Yes. So let me say something. Don't memorize strictly that the vector is a vector that is looking up. Okay. If the vector is given like a row and you are told to find this quantity, you can always figure out what comes out of it. Okay. But you should know this: the inner product, the result is always a scalar quantity, which means that if T is defined like this, you cannot find inner product because the result will come a 3 by 3 matrix, right? So this T here, so let's try to read this carefully. The language we use in this class, this is a vector because it's an arrow. T transpose is also a vector. This is vector, vector, this is equal to a matrix. See how we denote this one? This capital T, it's a matrix, so this means that this is not a scalar product. Similarly, we see that this step is a scalar answer. Now, we can, so inner product, it is written here, so I'm not going to write this again on the board, but this is what it is. We can define also the magnitude of a vector, okay? The magnitude of a vector magnitude of a vector, this is defined as the square root of T. Okay? So this is the magnitude of the vector, which means that in this case, what is the magnitude of T?
It's square root of 10.
That's true. So this is the square root of 10. Now, what is the magnitude of T3, this T3 which is here on the board? What is, and we can denote this like this actually, T3,
Square root of 5.
Square root of what?
Square root of 5.
Thanks, okay. This is square root of 5. So, this T3, where is this on the board? This on the board is this vector, which is 2, 1. So here we have 2, 1. And square root of 5 is in fact the length of this vector, okay? So how long is this? We use the Pythagorean theorem. And Pythagorean theorem, it states that 2 squared plus 1 squared, we get the hypotenuse squared. So with magnitude, or the inner product of a vector with itself, it is in fact the length of the vector itself. Okay? And I want to denote one important thing here, which maybe you are going to see this one a lot in the future. I like to think of matrices and also vectors as entities which are to some degree equivalent with complex numbers. Okay, I guess we know what complex numbers are. We don't have a we don't have a class dedicated on complex calculus, but there is a. You could take this one. We can offer this one as an elective course which is complex calculus, which does the same calculus that you do analytically that you are taking in the first year. But so again, in one sentence, I can say that complex numbers have an equivalency with matrices or vectors. Why we are saying it? We say this because, for example,
complex numbers have a magnitude too.
That's correct. What else? What about, tell me one complex number.
3 plus 4e. 3 plus 4e.
Just I. Yeah,
I.
Okay, so 3 plus 4i, that's true. Now, this 3 plus 4i, we can plot this in the Cartesian coordinate system, where on the x-axis we have the real part, and on the y-axis we have the complex part.
Right? Imaginary part.
Imaginary part, that's true. 1, 2, 3, 4. Okay, and we have here 1, 2, 3. So this complex number, this can be denoted here And we don't need to repeat all the essentials of the complex numbers, but I just want to make it clear for the sake of the equivalency, which if you keep thinking about it, you might have this understanding when you go to the third year, when you go to more advanced classes. So now here, so you said it has a magnitude. What is the magnitude of this complex number?
3 minus 4i.
No, the magnitude, it would be the length of this vector, right?
Oh, yeah.
And we know that 3 squared plus 4 squared
5.
is equal to 5 squared, right? So the magnitude here is 5, the length of this vector, that's correct. It has also the phase, ca faz. Numărul complex ca faz, la faza për kufizon seconding që krijohet me boshtin x-ën. So also try to find out what this angle is, it gives a phase, good. But now, when we discuss about the magnitude of a complex number c, it's equal to the square root of c, the product of complex conjugate with c itself, okay? Now, this is the equivalency between the magnitude of a complex number with the magnitude of a vector. Because what is the complex conjugate of this complex number?
3 minus 4i.
That's correct, 3 minus 4i. So then, when we do this multiplication, we write the following. Let's take this away. So, the magnitude of this complex number
plus 4 squared.
It's equal to 3 minus 4i times 3 plus 4i, and this would be equal to 3 times 3.
From the difference of squares, we get 9 plus 16.
That's better. Then you are correct. So we can do the difference of this, but we can also do it step by step. This is 9 minus 12i.
12i plus 12i.
No, wait
plus
a second. Minus 12i squared plus
12. No, just 12i, not squared.
12i, yes, we are okay, that's minus 12i plus 12i.
Plus 16.
Minus 16i squared. You are right, okay, but this cancels out. Minus 16i squared, and let's not forget the square root. I forgot that. You are right, I squared is equal to minus 1. I squared is equal to minus 1. Because this is I is defined. So here we get the square root of 9 plus 16. So we are left with a 5, okay? So, so this is one thing where you can easily observe the similarity or the equivalency between a complex number and the matrix. I want to stress this from now so that you keep this in mind, because when we're going to discuss later the determinant and the manipulation of the vectors, I want to bring this up because you will find this one very useful when we discuss the topics of signal and systems or manipulation of matrices in a higher dimensional space. Okay, so keep this in mind, I'll remind you a couple more times during this semester. Also,
Professor, shouldn't it be from minus 16i squared? You forgot the I squared, or did you just?
Yes, it becomes plus because Shiva, but I cut minus
minus 1, okay?
Nu te pașă, da.
No, that's fine. Don't worry. So this is defined as a square root
is minus 1.
Okay? As a reminder, this is how complex numbers are defined. But then, from last week, we said here in the class that with matrices, we can add them, we can subtract them, we can also multiply them. And even multiplication is not always defined. Why? Because some dimensions have to match. In order to enable element-wise pair multiplication between, like as we did here, we need the number of columns and the number of rows being equal. Okay, we know that much. But we said last time that the division by matrix is also not defined. Similarly, division by a complex number is also not defined. Okay, so here you can see a second equivalency between the matrices and the vectors. And you can take a note down if you are when you are writing now. You are going to see this equivalency showing itself in a wonderful way when we discuss about the eigenvalues. So you are going to see this once again, and I'm sure you might find it impressive. But for now, let's see this other equivalency, which is the following. What is, for example, 2 over 3 plus 4i? What is this? I mean, this division, which is up there, this is not defined, okay? Because we cannot divide with a complex number. So what do we do in this case? We just multiply with a complex conjugate the 2 and the denominator and the numerator, okay? Which means that we're going to get, so this is equal to
2 times 3 minus 4i.
So this number, we multiply this with 1. What is 1?
We conjugate 3 minus 4i.
That's correct. Okay.
And we divide it with 3 minus 4i.
Yes. So we multiply by 1. Okay. So this here, what is this? 3 plus 4i times 3 minus 4i. We get 25.
The square of the magnitude. It's 5. Yeah, 25.
Let's call it 25 for the moment. And then what about the numerator?
6 minus 8i.
That's correct. 6 minus 8i. And this is equal to 6 over 25 minus 8 over 25 times I. Okay. But why were we forced to do this? We had to do this because a division by a complex number is also not defined. Okay. Let's continue. So we defined. We saw how vectors are used in space. We defined the inner product. We defined the magnitude. And also, I can also add, since we discussed here the complex numbers, in principle, in more complex mathematical constructs, the magnitude, there are many quantities which can be described as vectors and complex numbers. For example, in quantum physics, if you want to find the probability of a specific state, okay, you don't need to know this one. At least maybe you won't often see this one. Electronics engineers, they might see this actually, but you as computer engineers, unless any one of you goes into quantum computing, you should know this, or but you might learn it again later. So the probability to calculate something is in fact equal to the inner product of a wave function with itself, which in principle it's equal to the phi transpose times phi itself. But often this phi, it is a vector for sure, but often it includes also complex numbers. So when you have complex numbers and vectors, you do them both. The column, you make it a row, and also you calculate at the same time complex conjugates. Okay, so you might see both this magnitude of a vector and the magnitude of a complex number. I'm just saying that quantum computing because you might find this closest with your interest of the department you have chosen. But these two things you might see them in a slightly more complex aspect in assuming when you have vectors which include also where the entities of a vector include also complex numbers. Now probably it's time to move to a further topic. So we define the length of a vector, and then we can define also a unit vector. A unit vector, it's a vector that is normalized, okay? So we can call it this way, and probably, maybe I can erase this part. And this complex number division, we can also take it out. So let's define here, we have unit vectors. And when we discuss about unit vector, we can define a unit vector for any vector, okay? So unit vector is defined as when the magnitude of t is equal to 1. So this is unit vector, okay? And for example, what is a unit vector? it's simply it's 1, 0. Okay, 0, 1 is another vector. Also, in if the vector is in R3 space, this can be 1, 0, 0. Okay. Similarly, we can have 0, 0, minus 1. So these are all unit vectors because the magnitudes are all 1. Okay. And we can also have 0, 1, 0. Okay. Also, this can be 0, minus 1, 0, 0. So these are all unit vectors because the definition is simply what is on the board. So, but then unit vectors, we might see them used when we normalize a vector. We call normalize, and the concept of normalizing a vector, it is very important for large data analysis. The reason is the following. Imagine, for example, that you have to compare two samples, okay? You have to compare two data sets. And, but in order to compare those, the magnitude might be different. For example, what example I can provide here? Let's assume that you have a distribution. I think we started with a distribution last week when we defined the vectors. We said that we tried to draw the histograms, right? I said, what is your expected grade in this course? You told me I'm going to get an A, a B, or a C, and we were trying to draw a histogram or the grade distribution. And often, what you might find, because this linear algebra course is a very useful course, and you might prepare yourself into comparing, for example, let's say we have a vector so we have these two vectors, okay? So you have a data, and this data is represented by these quantities. But then, how can you compare those? They are too much off of each other, okay? Or a better example, in fact, is one where you might be interested into observing the correlation between two data. So you can take note now. I can give a lot of examples, but it might take too much of our time. But in this case, if you have to compare two data sets that look like this, often, okay, feature vectors, okay, you can write this down, and I have to explain this to you, what is this feature vector, so that when you see this in the future, you can immediately remind something. So a feature vector is a vector which tries to extract basic information about something. A feature vector, for example, is the simplification of an image that could have a Mercedes and a Ferrari. So these are complex entities full of numbers, but you can extract a feature vector which you then compare. But when you compare these vectors, like which could end up to be this or this, what is the best is we can normalize those, make them all the same magnitude, and then we compare those, okay? Because we could have also a vector here which is 50 minus 48, okay? So here we have three vectors and we want to compare them. The magnitude is very different because this one, this 0.9 and 1.1, is a vector which is somewhere here, okay? It's somewhere this length, which has square root length. But 101 is going to be a vector which will take 100 units this way along the x-axis, 99 units all the way up, and we get a huge vector, and it's hard for us to compare them. So in this case, what do we do? We normalize all of these. How do we normalize? In order to normalize these vectors,
We divide by the magnitude.
Say it again?
We divide by its magnitude.
Exactly, yes. Yes, that's correct. We divide by the magnitude, and then the length will be 1. So then, when you compare those, we just look at the angle that is between these two vectors, okay? So it looks like to some degree, we can calculate this for sure, that if we normalize this vector with this, they are going to be relatively close, okay? Because this is like, kjo është gati 25 gradë, që se shkojmë, mëshina ime në Thaland është gati 25 gradë, në poshtë njëseve. Edhe këtu diku aty është. Kurse këtu këtu 50 minus 48, kjo është kjo dhe minus 45 gradë. Në që kjo është gati 45. Në lidhje me boshtin e x-eve, kjo dhe diku minus 45, që këto të dy mund t'jenë, we are using the equivalent sign. They are not equal, but they are almost equivalent. But these two, they are not equivalent. Okay, I mean, or the second with the third. So, by definition, if we want to normalize, we divide it by the magnitude. It's best if we do an example here. So, why do we normalize it? Because we may want to compare different feature vectors that are in different orders. What is the order of this? What is this 101 and the 99? This is in the order of 10 to the power 2. What is the order of this? This is 10 to the power 0. Okay, because 1 is 10 to the power 0. What is this? This is something like 10 to the power 1. Okay, so we have three orders of magnitudes. We could even have a vector which could be 1200, 900. So this vector, this is a vector in the order of 10 to the power 3. So of course we can compare them right away, but we can normalize them and then have a look at for the second time. Now, let's try to find a unit vector, or let's normalize this 6, 4. Let's normalize 6, 4, which means that we can denote it or write this in probably this piece of information, and actually I can try to adjust at a late stage without doing too much damage. So we have this 6, 4. Let's call this T.
Professor, our time is running late.
Say it again.
Our time is running late from schedule.
Okay, you have another class?
No, we can stay for a little bit. I was just saying it to inform you.
Okay, okay, that's true. Time has passed, but allow me a few more minutes and we'll come to a closing very soon. Okay? So let's assume that here we have the vector 6, 4. We can define a unit vector u, and unit vectors, we write this with a cap like this, okay? This is equal to vector t divided by the magnitude of t, okay? So this is how we can define, and similarly, this is equal to t, vector t, divided by the inner product with itself, okay, square root. And now let's see what we get. This t itself, this is equal, so let's find first the magnitude. What is the magnitude of t? We do the following. We do the square root of 6, 4 times 6, 4. Okay, so what do we get here? 6 times 6, 36 plus 16. We get 36, 16,
52.
Who can help me? 52, huh? 52. Square root of 52. Okay, so this is 1 over the square root of 52 times t. What is t? T is 6, 4. 52, can you simplify this further? 52, is it divisible by 4? 52, we get 4, 12, yes we can. So this
13.
52. This is equal to, we get here square root of 4, and this is it 13?
Yes.
Yeah, it's 13.
Okay, 6, 4. So this is equal to, we get 1 over the square root of 13 times 3 and 2. Okay, so this is a unit vector along the direction of t. Now, we can provide another example. Let's assume a vector v, which is equal to 1, -1, 2. This is a vector v. Then similarly, we can define a unit vector u along the v, which is going to be equal to vector v divided by the magnitude of v, which ends up into being. So what is the magnitude of v? The magnitude of v is equal to the square root of 1 minus 1, 2, multiplied with 1 minus 1, 2, and this is equal to 1 times 1, 1, plus 1, 2, plus 4, 6. So this is square root of 6. Then this is 1 over the square root of 6 multiplied with 1 minus 1, 2. So this is the answer. We can leave it here, okay? That's enough. Or we can also, we know that the multiplication of a vector by a constant, we multiply with this constant all elements one by one. So here we're going to have 1 over square root of 6 minus 1 over square root of 6 and 2 over square root of 6, okay? So these were the unit vectors along a specific direction. Now, do you have any question? Anything which is not clear?
Nothing.
Okay, if this is the case,
A
probably...
little bit about normalization.
Yes.
I didn't understand that.
Okay, normalization, we can define it as the, let me think. So when we want to compare different vectors that are of different orders, okay, it is best, or it is often used in data analysis into obtaining a unit vector along the direction of a specific vector. Okay, and the normalization, the way to do it, we divide this vector by the magnitude. For example, here we have this vector 1 minus 1, which we drew it here. Okay, what we can do is that we draw a circle with radius 1. Okay, let's draw here a circle with radius 1. So we have this, and for example, we have also this vector which was 3, 4. 3, 4. What is 3, 4 unit vector? It is in the same direction with this vector, but the tip, it ends at the outer boundary of this circle with radius 1, with radius unity. We have this other vector which was 1 minus 1, which is down here. Okay, it's a little out of this circle, but the unit vector that along this vector is going to be, you know, I cannot, maybe I'm trying to do a good drawing, but so we can also have another vector which is extended this way, and by dividing this vector with its own magnitude, we obtain a unit vector which is going to have the same direction up, but it will end at the boundary of a circle with radius unity. Is it clear?
Yes, so we find the unit vector.
Exactly.
In normalization.
Yeah.
Okay.
Okay.
Thank you.
Okay, so yes, we can stop this here if you have no more questions.
Professor?
Yes.
When we want to find the magnitude of a vector, do we have to always write down the transpose times the matrix? Can we square? Can we just square the elements of the matrix instead? Because it's the same thing.
Yes, you can, but well, I say you can, so that, but in order so that you don't forget it, it might be good to follow the regular procedure.
Okay.
Yeah, in principle, yes. I
Okay.
mean, yeah. Okay. So I want to thank you for your